Hey guys, today we're going to be looking at evaluating improper integrals, and this is for AP Calculus BC students. So we've seen integrals that have real numbers in their bounds, right? But what if we're dealing with something like this? The integral from 1 to infinity of 1 over x squared dx. Well, infinity is a concept, not a number. But whenever dealing with improper integrals, and an improper integral is an integral that has one or both limits infinite, or has an integrand that is unbounded in the interval of integration, we can rewrite the integral as a limit. So I'm going to rewrite this as the limit as some variable, let's just say b, approaches infinity of the integral from 1 to b of x to the negative 2 dx. And now what I'm going to do is simply integrate. And now I'm going to get the limit as b approaches infinity of negative 1 over x from 1 to b. And now this equals the limit as b approaches infinity of negative 1 over b minus negative 1 over 1. And this equals the limit as b approaches infinity of negative 1 over b plus 1, which is simply equal to 1. And that's how we properly evaluate these improper integrals. You always have to write it as a limit expression, because if you don't, it's technically incorrect, because infinity is not a number, it's a concept. So let's look at another example. What if I have the integral from 1 to infinity of 1 over x dx? Well, I'm going to rewrite that as the limit as b approaches infinity of integral from 1 to b, 1 over x dx. Then I integrate, and this becomes the limit as b approaches infinity of ln of the absolute value of x from 1 to b. And now this becomes the limit as b approaches infinity of ln of b minus the ln of 1, which is 0, so just ln of b. And now I have this, and this is simply equal to infinity. Now, what does this mean, though? I have an integral, but it's equal to infinity. So we found the value, and whenever an integral, is it equals infinity or negative infinity or can't be determined, we say that this is a divergent improper integral. Divergent improper integral. And the one we had up here, we would call this a convergent improper integral because it converged to a real number. Okay. So those are the basics of improper integrals. Now let's also do a couple of examples here. So I'm just going to look for a couple of examples that we can do. And to me, these are some very good examples that we can do. So first, let's try to evaluate the integral from 0 to 4 of 1 over the square root of x dx. Now, this looks to be a normal integral, right? I have real numbers in my limits of integration. But this is the problem. Root x equals 0 at x equals 0. And look at what's in my bound of integration, 0. So this is going to be a problem. So I have to rewrite this as a limit expression. This becomes the limit as b approaches 0. And b is going to approach 0 from the right because I'm going from 0 to 4. So that interval, really, if I started at 4, I'd be approaching 0 because I'm still in that interval, right? So that's going to be from the right. Integral b to 4. And then rewrite this as x to the negative 1/2 dx. Now, when I take the integral, this is going to be the limit as b approaches infinity, or sorry, b approaches 0 from right to left of 2 root x from b to 4. And now I'm going to get the limit as b approaches 0 from the right of 2 root 4 minus 2 root b. And this is going to be the limit as b approaches infinity, or sorry, I keep saying infinity, approaches 0 from the right of 4 minus 2 root b. And simply, this is just going to be 4, because we just plug in that 0, and really we're going to get 0 there. So the answer to this integral is that it actually converges, and the answer is 4. Now, let's do another example. Let's do, what should we do here? Let's do the integral from 0 to 2 of 1 over x minus 1 to the 2/3 dx. All right, I'm going to let u equal x minus 1 du dx equals. Now, actually, before we do this, we should rewrite this as a limit expression. So this in a limit expression is the limit. Now, let's see what's undefined. X minus 1 to the 2/3 will equal 0 at x equals 1. So notice what we have to do for this one. We actually have to break it up into two integrals. So before we do this, we should rewrite this as the integral from 0 to 2 of 1 over x minus 1 2/3. And whenever you're unbounded places within the interval, you have to separate it there. So I can rewrite this as the integral from 0 to 1 of 1 over x minus 1 to the 2/3 dx plus the integral from 1 to 2 of 1 over x minus 1 to the 2/3 dx. Okay. So now what can we do? Well, I can rewrite this as the limit as b approaches 1 from the left this time. And we can see this is from the left of the integral 0 to b, 1 over x minus 1 to the 2/3, plus the limit is c approaches 1 from the right of the integral from c to 2 of 1 over x minus 1 to the 2/3 dx. And now I evaluate. So now I'm going to let u equal x minus 1 for both of these. And du dx will equal 1, du dx will equal 1. So therefore dx equals du for both of them. But remember, I have to change my bounds of integration, right? So this is now going to become the limit as b approaches 1 from the left, integral from -1 to b minus 1 of u to the -2/3 du plus the limit as c approaches 1 from the right, integral c minus 1 to 1 of u to the -2/3 du. All right. So this is, the proper way of doing this. It may be, tedious, but this is how you have to do it. And now I'm going to evaluate. So this becomes the limit as b approaches 1 from the left of, and this is going to be 2/3, sorry, this is going to be, we're going to use the power rule to evaluate this integral. So we're going to add 1 to the top. So that's going to make that 1/3 and then 1/3 on the bottom. So that's going to be 3 cube root u -1 to b minus 1 plus the limit as c approaches 1 from the right. And then the same thing here, 3 cube root u from c minus 1 to 1. Now we gotta, still be repetitive. This is gonna be limit b approaches 1 from the left of 3 times the cube root of the cube root of b minus 1 minus, now what is the cube root of -1? That's gonna be -1. So this really becomes plus 3, right? Now we have plus the limit as c approaches 1 from the right of 3 minus 3 cube root c minus 1. Now when we evaluate this, we can see that this is simply going to become 3 plus 3. And that equals 6. So you can see that, these integrals are a little interesting, right? We have to separate them if there is an unbounded number in our interval. But then if they're at the endpoints, we can treat those differently. So this was a review of improper integration. Hopefully everyone understood it. And in next video, we will go over a method for approximating solutions using Euler's method.